Hello, my name is Shenkong Li. I am Professor of Radiology from University Hospitals Case Medical Center. Me, along with colleague Ray Music, Dr. Music, will be covering topics surrounding nuclear medicine imaging. So what we're doing are actually using radioactive imaging agent. We inject them into the body, and the gamma camera outside the body will catch the radiation emitting from the body for image formation and image reconstruction. So these are the topics we'll be covering during this lecture, and we will cover these in the next lecture. Here is a periodic table most of you are very familiar with. What we're doing is we're using radioactive isotope of the stable elements. For example, carbon, nitrogen, oxygen. These are the building blocks for organic compound. And we are using radioactive carbon such as carbon-11, radioactive nitrogen such as nitrogen-13, radioactive oxygen such as oxygen-15, and radioactive fluorine such as fluorine-18. In addition, we also have radiometals here such as copper-64, technetium-99, rhenium-186, lutetium-177. We will use a chemical structure called a chelate to hook them up, attach them to the targeting moiety for us to do imaging. So where are these radionuclides coming from? Well, we can group them into two groups. One is coming from the nuclear reactor, such as molybdenum-99, iodine-131 commonly used. The other category is coming out of the accelerate, such as the cyclotron. We will talk both of this. This is a diagram of a nuclear reactor. We do not have one on campus. We do not. Purdue has one, and University of Missouri has one. And what's happening inside nuclear reactor are those high Z elements. They are not stable. The nucleus is not stable. It will disintegrate to form new elements. And some of them, still radioactive elements, are very useful for medical use, which we will talk about. Going from the last slides, inside nuclear reactor, it is a neutron-rich environment. So neutron will hit the nucleus, such as that of uranium-235, and it will disintegrate to produce daughter ones that are still radioactive, and some of them will be useful for us to do imaging. And this summarizes what I just said. So within the nuclear reactor, it will produce neutron-rich radionuclide. Neutron-rich means it has too many neutrons to hold the nucleus together. It will decay by emitting beta, which is negatively charged electron. In contrary, within cyclotron will produce neutron pool. Those radionuclides, they do not have enough neutron within their nucleus, so they are also unstable. They will decay. And there are two equations, as the last slide showed you. In a neutron-rich environment, such as the nuclear reactors, what's happening is, for example, we have an element here, which is phosphor 31. When it was hit by a neutron, it becomes phosphor 32 and emit a gamma ray. So one neutron goes into the nucleus, the Z number is the same, so it's still phosphor, but it is radioactive now. So is chromium from 50 to 51. One neutron comes into the nucleus, it becomes chromium 51, and it emits gamma. And this chart shows the efficiency, the so-called fission yield within the nuclear reactor. And this is a semi-log, scale plot. This is about 1%, this is 10%. So as you can see, for molybdenum, cesium, they are pretty good in terms of efficiency. Iodine-131, the most commonly used nuclear medicine radionuclide over there, it is okay. It's not great, but still useful. Down below, efficiency is too low. It won't be useful. Coming out of the nuclear reactor, we have molybdenum 99 and some of the iodines. So how are we going to use them within our clinic? Well, this is a generator which we have at our clinical department of nuclear medicine. And within this generator, you will hose parent radionuclides such as molybdenum, which has a longer half-life. It will decay into technetium-99m, which we will talk about next. It is the daughter one that is used here in the clinic of nuclear medicine. So what we do each day is you put some saline, milk it, and you take it out. So here is the decay scheme. So molybdenum 99 half-life is 60 hours. Half-life means the time it takes for a radionuclide to decay to half of its initial activity. So this is pretty long. Molybdenum 99 is coming from nuclear reactor, as we covered before. When you put it inside a generator, and you can place it in any clinic, nuclear medicine clinic, and it will decay mostly 88%, close to 90% into clinical use for radionuclide technetium-99m. Its half-life is actually good. It's not too long, not too short, 6 hours. Technetium-99 will be further decaying into technetium-99 with a half-life of 200,000. This is something we don't need to worry about. This is the key here. You need to remember. It's the technetium-99m decay into technetium-99, and by doing so, it will emit a gamma photon for image. And here is a diagram to illustrate the half-life as we were talking about. At time 0, if we start fresh from cold, all we have is 100% parent molybdenum 99, 0 for the daughter. As the parent decays, it's a longer half-life. The slope is not very steep, and the daughter grows up exponentially. At some point, the amount of parent and the amount of daughter will be equal. This is the so-called equilibrium. So for technetium-99m and molybdenum 99, it's about 23 hours. So after one day, as you can see that technetium-99m reach peak. This is when you put some saline to milk it, then for clinical use. Then about another day, it reaches peak again, then you milk, so on and so forth. But of course, if the parents goes too low, it will not be useful, and it will be the time for you to make an exchange, meaning that you will ship out the old generator, take in a new fresh generator starting from here. So it's about a few weeks. So this is the equilibrium we were talking about, and actually you don't need to calculate this. In every nuclear medicine clinics, there are charts put on the wall with a time scale, so you would know when the efficiency will be and when, most importantly, when you need to make an exchange. Now we have the radionuclide, right, going through nuclear reactor and the generators in the clinics. What are you going to do? Well, we're going to use it to tag to our imaging agent. So there will be some labeling going on. And by labeling, there will be some chemical bond to attach the radionuclide to the imaging agent. So let's briefly review some of the chemical bonds that we have learned before. First one is ionic bond. Something negative binds with something positive, electrically charged, and the chemical bond can be very strong. But the other one is the so-called covalent bond, mostly applicable to the organic compound, and in which two elements will donate one electron to form a pair to be shared, so the chemical bond can be very strong. The other one, last, most relevant to this talk, is the so-called coordinate covalent bond, so in which one of the pair will donate two electrons to be shared by the other one on the orbit. It also can be very strong. So for labeling radium metal, as I mentioned previously, the key thing is a chelate or a cage to house your radionuclide. For example, technetium-99m, indium-111, yttrium-90, gallium-68, or lutetium-77. How the chelate is going to work? Let me use one example. This is a DTPA, commonly used. So you have a radium metal here, mostly positively charged. It will attach more or less to the negatively charged. Here, look, there are carboxyl groups. And nitrogen has an extra pair of electron, which will be shared by the radium metal. There is a vacancy here. So this will form a coordinate covalent bond. So this cage can tightly hold your radium metal for imaging or for treatment. And you don't want radium metal to flow freely inside your body or in the circulation. Now let's begin to talk about imaging. So now you radio label your imaging agent with radionuclide, radium metal or otherwise. Inject into the body. When the radionuclide decays, it will emit gamma photon, gamma ray in this case. So the gamma ray is not visible, but it's quite energetic. It will interact with any material along the path, either going through our body or going through any other materials. So in summary, two things happen. One is the so-called photoelectric effect. The other one is Compton scattering. So for photoelectric effect, the incoming gamma photon, energetic, interact with the orbiting electron of an atom. So the electron will be ejected, and the incoming gamma photon deposit all the energies here, and it's gone, disappeared. So you ended up with an electron and positively charged element here. So this is the ionizing radiation. So basically the photons, the not visible energetic gamma photons shooting through our body like bullets. So the other one is more of a concern for medical imaging, is Compton scattering. Incoming gamma photon, again interacting with orbiting electron, ejected, but the gamma photon did not deposit all its energies. It deposited some energy, it loses some energy as a consequence, and it changes direction. Imagine if this scattered gamma photon goes out of the body, reach the gamma camera. It will represent the wrong information. It will degrade the image resolution as well. So this is something we need to correct. We will talk more about this. So to those of you who wants to know more about Compton scattering, here is a formula, the so-called Klein-Shiner, showing the relationship possibilities. This is beyond the scope of this lecture. So again, those of you who are interested can certainly read more outside class. So after this introduction, let's talk about gamma camera. This is the architecture of the so-called Anger camera, first devised by Anger last century, 1956. Boy, that's more than 60 years ago. Although each component of the camera, such as the collimate, not much of a crystal detect, certainly PMT, front-end electronics, and the computer system, computer algorithm, all vastly improved, but the basic architecture of the camera remains exactly the same. So we said we're doing radionuclide imaging. We inject radioactive agents inside the body. It will radio decay and emitting gamma photons going out. And the camera will catch those for imaging. So let's go through each component one by one. First encountered is the collimate. It's actually quite heavy. I don't think this person can lift up like this. But it shows you the relative size, provided the guy has a normal build, maybe 5'10"-ish. So over the years, we use different collimate in the nuclear medicine clinic. And nowadays, two of them are commonly used. One is the parallel hole collimate, one is the pinhole collimate. We seldom use convergent or divergent collimate. So parallel hole meaning that the openings of collimators are like parallel. So only those gamma photons that are parallel to the openings will go through. Those not will be stopped, that it will have a meaningful image. Pinhole collimate is similar to those cheap cameras you used to be able to buy in the supermarket. It does not have a lens. It's a small hole. The geometry is inversed. This inversion, because of distance, gives you amplification. So if you have a small object closer to the aperture of the opening, and you will get amplification due to geometry. So parallel hole, it's designed so that you only allow those gamma rays parallel to the openings to go through. Here we show some details here. So these collimators are packed like honeycombs and separated by the so-called septors made of heavy metals, lead, tungsten. That's why I said it's very heavy actually. You probably not be able to pick it up. And it has different parameters for trade-off. So some of them are for low energy gamma photons. So different radionuclide, when they decay, they're emitting gamma photons with different energies. Some of them are low, some of them are high. For high energy gamma photons, you need thick septors to stop them so that there will be no penetration or crosstalk, so your image will be better. And also, if you want higher resolution, you need those long collimators. Going through the long holes, you further ensure that only those parallel to the holes will go through. It will make more sense as we go through. One example here. We have a point source going through a parallel hole collimate. So ideally we should have one point here, but we don't. So in the middle, many gamma rays from the decaying point source will go through this parallel hole collimate because they are more or less parallel to it. Towards the edge, because of the angle, these gamma photons will be stopped by the septors. So you have less signal. So instead of one point, you have a profile, the so-called point spread function or line spread function to describe the spatial resolution. So FWHM stands for 4 with half max, defines the spatial resolution. So you can move things around. If you place the point source close to the surface of the collimator, as you can see, Only those in the middle will go through the parallel hole. So the profile is narrow. Image will be sharp. You have high resolution. In the contrary, if you pull it away, many photons will be able to go through the parallel holes, and only those really at the edge will be stopped. So you have a much wider profile or lower resolution. So position matters. Keep that in mind. So here is a calculation of the position, the distance between object to the collimate. When they are very close, system resolution is very good. You can resolve small objects. When you move up, is a leap, low energy, all-purpose parallel hole collimate, or low energy, high resolution or ultra high resolution. You can see that when you pull it away, the resolution gets worse. Efficiency, mostly they are fine, different collimators in terms of distance between the collimate object. Only exception is pinhole. As I said, if you pull it away, you got a much bigger amplification, larger amplification of small objects. But you really cannot do this, because when you pull it away, the sensitivity, the efficiency goes down dramatically. So continuing on pinhole collimate. Pinhole collimate, due to the inverse geometry, you get amplification, which allow you to see some of the details, such as lesions within the thyroid or joints, extremes in your hands, thumb. Or you can image small animals, such as mice and rats. We'll talk about this next time. So after collimation, what's next is the crystal detector. Why do we need a crystal? Well, the gamma rays, as I said, energetic. They are not visible. So to form an image, you need something dense to stop them. Convert them into visible light photons for you to do imaging. So what's happening is the process called scintillation. So through is a component of photoelectric, you have those electrons, and they will interact with the nearby atoms. This tightly packed, dense material called crystal interact. So the atom will vibrate, release energy in the form of visible light photons, and after a few iterations, the income gamma photon will be gone and turn into those light photons. And a few parameters concerning the scintillation crystal. So for most gamma camera, we're using sodium iodine doped with thallium. This is the crystal. Density is high, but not as high as BGO LSO. These are for PET imaging, because light photons from PET imaging, the energies are even higher, so we need more dense material to stop them. However, the light output for sodium iodine crystal is very good in comparison to BGO LSO. The other thing is the thickness. So you need a thick crystal to stop high energy gamma photons, to give you good efficiency. But if they get thick, remember those scintillations, they bounce back and forth. At a point, it can become a halo, so you lose some of the resolution. So for high resolution, you need a thin crystal. Of course, for the problem of the thin crystal is the efficiency. Higher energy gamma photons will shoot through without scintillation, so you will lose some of the efficiency. Next, very next, after scintillation crystal, what you need is PMT, another conversion. So the scintillation crystal will convert gamma photons into visible photons. The visible photon will enter the face of the PMT, which is made of photocathode. It's a cathode. And once the photon hit the photocathode, it will emit an electron. and it will going through an array of anode or dynode, what we call dynamic anode, to get signal amplification, which is needed so the output current will be strong for input for further imaging process. So here is what I just talked about. First you have a collimate in front of patient. Next you put crystal, scintillation crystal next to it, and very next are those PMTs. They have their size, but they are packed behind the crystal detect. Then the after amplification from this array of diodes, you have electrical signal which were going through pre-amplification for further use. Here is the further processing. So after PMT, there is something called analog to digital conversion. So you will convert the electrical current coming from PMT or preamp into digital signal, feed into either computer or circuits. And in the next slides I will talk about how we're going to position the image event and also determine the image intensity. These are blank scans, nothing in the field. It should be like this, but they are not. So you need some corrections to make them uniform, but I did this intentionally just to show you where the PMT, this array of photomultiplier tubes, are put behind the crystal, and they have their finite size. They are not small. So how are you going to image? Let's say that if one gamma photon hit the crystal detect, right, it do scintillations, and the nearby PMT will got response signals. Those further away will get less response signals. So how do you determine X and Y coordinates? Well, you calculate your center of gravity among all those TMPs to determine the position. As shown here, once you determine X, Y, you will be able to locate them within the image array where it is. Separately, there is another channel to determine the energy of incoming gamma photon for further processing by this unit called PHA, pulse height analyzer. It will be able to discriminate the energy of incoming gamma photon. When you have everything, you can plot your spectrum. So here is a spectrum, and it shows the energy of the gamma photons as determined by PHA. I will use indium 111 radionuclide as an example. When indium 111 decays, it emits two groups of gamma photons. One group with the energy centered around 171,000 electronic volt, keV. That's the unit. Don't worry about it. The other group, all the photons will have the energy centered around a higher peak, the higher energy, 245. So if there's nothing in the way, you will have only two peaks. But going through the body, because of compton scattering, you ended up with those shoulders. The dotted line shows the photons that are scattered either once, twice, like the lower shoulder. These are 3 times, 4 times, maybe 5 times. We do not want those scattered photons in the image because they represent wrong information. They will decrease the spatial resolution, image sharpness. So on the camera, you'll be able to do this by setting up the so-called photo peak window. So you put this energy window. Basically, you only allow those gamma photons in the yellow color have energies to go through. Then you will reject those outside the window, you consider these to be scattered photons. So you can do that. So here I should have shown you a dynamic image of the acquisition on the screen, but instead this is a schematic diagram. Let's go through this. So this is what you have. When the first photon comes in, it interacts at a certain position. Then calculate the center of gravity to locate x and y. The position is here. The separate channel will show you the energy of the gamma photon. Then it will go through the digital back to analog conversion so that you can have signal to be displayed on the screen. Second event coming in at a different position display. Third event on the same position. So at the same position, the imaging intensity will be stronger, so on and so forth for the dynamic process. So again, going back to the spectrum, right? We said we don't want these scattered photons. One way to do this is to setting up energy windows. But even within the photopeak windows, look at this triangle here. These are the scattered photons. And we need to correct these further. Well, the other thing, remember the photoelectric effect? Incoming gamma photon never came out of the body. It's gone. And for quantitative analysis, we need to compensate for this. So in the end, we will talk about correction for tissue attenuation. All right. So after gamma camera, now let's talk about imaging. So using gamma camera, we can do two things. One is planar imaging, similar to planar X-ray. So camera is stationary, it's not moved. So you do one projection to collapse three-dimensional distribution of radionuclide inside the body onto a two-dimensional image, very much like X-ray, as I said. We can do bone scan for this, and we can do some of the other scans. Or you can also rotate the detect head around the body, very much like CT, to do tomographic imaging, 3D. So different from CT, CT is doing circular orbiting. You have a ring, right? So X-ray tube that detects opposite to each other, rotate around the body. But since position matters, as we show, if you put the point source closer to it, move it away, it matters in terms of spatial resolution. So what we want to do is we want to place the gamma camera to the human body contour as close as possible. So in a sense, we are doing contouring imaging because the position matters. So we need to correct for this before we do reconstruction. So speaking of reconstruction, so you guys are very familiar with this coming from CT. So this is a phantom, two point source or line sources, different angle, different projections will give you different profile. Put them together is a sinogram, looks like spaghetti. So to get image back, you need to do reconstruction in terms of projection. But for the simple back projection will not do the trick, as you already learned from CT. So what you need is filtered back projection, very much like what you've gone through in CT. So the field used is ramp, different parameters. Since you're very familiar with this topic, I will not elaborate. Instead, I will talk more about the so-called iterative reconstruction. So this is needed for nuclear medicine because we are count starving. Yeah, we are count starving comparing to CT or MR. I will explain why. And some of the low dose CT are also count starving. Instead of back projections, they also use iterative reconstruction. So it will start as initial guess, can be anything, can be a blank image, uniform. Then you do forward projection to get its sinogram. You convert this sinogram, you compare this sinogram with measured sinogram. then you will get a correction factor. You use this to correct your guess, and going through another round of iterations, so on and so forth. Then you will set up a threshold each time you compare your guess with the forward projection of your guess with the measured sinogram. You will set up a threshold. If the difference is small enough, you will stop. Now we have gone through everything, right? Radionuclide production, radio labeling, and each component of the gamma camera, from collimate all the way to AD-DA conversion. And we've also gone through image reconstruction. So now you have everything. So what do you care about? Well, we care about two things. One is for the system, for any imaging system, we care about two things. One is resolution, one is sensitivity. Resolution means spatial resolution. We already talked about point spread function, line spread function. Here we will talk about another thing, which is modulation transfer function. Before that, let's talk about more about spatial resolution. So each component in the gamma camera will only degrade your resolution. You have intrinsic resolution, collimation, and you have even reconstruction will degrade your spatial resolution. So overall, the system resolution will be the mean square root. So remember this. Here's one example. So your collimate different parameters as we talk about. The length, long for high resolution, low for short for lower resolution, and high energy. The receptors have their width. So from these parameters, you can calculate the resolution. As I said, besides line spread function or point spread function, you can use MTF, modulation transfer function. So for each image, different frequency component have different response through the system. So this is probably sometimes more useful. At this point, I will question you. What is the relationship between a point spread function and modulation transfer function? Or what is the relationship between line spread function and MTF? Think about this. And a line spread function or modulation transfer function are descriptions of an imaging system under noiseless conditions, ideal conditions. In reality, you have many things to worry about. So for sensitivity, in layman's term, when we talk about sensitivity, it's how sensitive it is, how weak of a signal you can detect. For medical use, how smaller of a lesion you can detect. So it has everything to do with efficiency. Again, each component in the system has its own efficiency. Highest efficiency for each of them will be 100% highest efficiency, which is 1. If this is 1, it will not degrade the system efficiency. In reality, each one has efficiency below 100%. So the overall, if you multiply them together, the overall system efficiency will be lower than each of them. For example, collimate has its efficiency. LEAP here, low energy, all purpose parallel collimate. Look, 1 out of 10,000 photons pass through. Only 1 out of 10,000 photons pass through. That's why nuclear medicine is sometimes called unclear medicine, because we're constant starving. And that's why we need iterative reconstruction. Otherwise, filtered back projection will be too noisy and full of image artifacts. You remember that. Now, we talk about the other corrections we need to make. So as I said, due to photoelectric effect, right? Incoming image intensity is this. going through a piece of body, a tissue showing here as a cube, it will be attenuated. And this mu is the linear attenuation coefficient, very much like the mu in CT. The difference is this is to the energy of gamma photons, not X-ray photon. So this is uniform. Inside the body, it may not be uniform. That's okay. We can do a CT scan. CT gives us density. For different density, we can convert them into mu, different mu's, linear attenuation coefficient. With that, we can do attenuation. We need this for quantitative analysis. One example here. This is a cylinder, phantom, filled with water, radioactive water. Should be uniform, but it's not because we didn't do attenuation correction. On the edge, it's okay. In the middle, it gets attenuated. We need to correct. The other thing I need to ask you is those ring artifacts. What are those? How are they formed? Think about this. If you know the answer, please email me or Dr. Wilson. So we will do attenuation correction. First order, chain. Assuming water or body tissue, so the coefficient is 0.12. So this is actually pretty good after correction. But if we use a higher attenuation coefficient, let's do 1, we will overcorrect it. As you can see, the object becomes smaller than what it really is. Now going through everything, you may ask me, what are we going to do? Well, use gamma camera, we can do a thyroid scan. Radioiodine, iodine 123, iodine 131, all natural substrate for sodium iodine importer, a transporter we have in our thyroid. It will transport radioiodine or cold iodine against its concentration gradient, so we can see the thyroid uptake. Sulfur colloid labeled with technetium 99M. You can also do imaging. Some of you may heard about the MEBI scan. Technetium 99 labeled cysteamine to mimic calcium uptake, used for myocardial functional imaging. And you have lung scans. And the DTPA, the chelate, you can aerosolize it. You can inhale radio gas for lung ventilation scans, and there are many other scans.